Okay, hi everyone. I just want to talk about polynomials for a little bit. Just highlight some of the most important parts of the chapter. So first of all, you should know what polynomials are. Like that's a polynomial, and even this is a polynomial. This kind of polynomial we call linear, and those will be really important. They'll correspond to eigenvalues for us. And here we'll call it quadratic, and those will be important. Their presence will show that sometimes a real vector space and a linear map on a real vector space will not have even a single eigenvalue. So you have to bear those in mind. Now, any other, like if you started with like, 4x to the third minus 2x squared plus x minus 1, actually what we're going to do is we're going to see in this chapter that will factor into something like x minus lambda 1, x squared plus bx plus c, where this has no real roots. It could be like that, or it could factor as x minus lambda 1, x minus lambda 2, x minus lambda 3, where now lambda 1, 2, and 3 are all real numbers. So that's how it would factor over the real numbers. Over the complex numbers, then it'll always look like this, but now the lambda j's might be complex numbers. Okay, in particular, this quadratic would then split apart as a complex number and the complex conjugate of that complex number. Okay, so let me just do another example. So for example, you could have x minus 2, x plus 3 squared, and then x minus 1 plus I, and x minus 1 minus I. And that would be the factorization over c of this polynomial, which would have degree 4 if we expanded it out, okay? And why don't we just do that? Let's expand it out. We'll start here. We'll get an x squared term. We'll get a minus x times that, and a minus x times that. So let's see, we're going to get minus 1 plus I x, and then also minus 1 minus I x. And then we're going to get a plus those two multiplied together, so plus 1 plus I, 1 minus I. And this will all work out so it'll be real in the end. So this piece will be minus x minus ix minus x plus ix, and those will cancel. And then here we'll have a 1 plus I minus I squared. So these will cancel, and then the I squared will become negative 1 to become a plus. A minus negative 1 is a plus 1. And that one, and we'll have minus 2x's, and we'll have the x squared from before. And so it'll be x squared minus 2x plus 2. So over R, the polynomial would not factor like this. It would factor like this: x minus 2, x plus 3 squared, x squared minus 2x plus 2. And that's it. That's the best you can do. That will be really important to us. We will really need to know these quadratic factors. Now, when will this quadratic factor actually split as real roots? Remember, the quadratic formula is like minus b plus or minus the square root of b squared minus 4ac. But if a is 1, then, and it would be divided by 2a, but if a is 1. And so what really matters is that these roots, these are the two roots, one for plus and one for minus. What matters is whether b squared minus 4c is negative. If b squared minus 4c is negative, then we get imaginary roots. Okay. What is that word root or 0? So let's say we have a polynomial p of x equals 3x to the third minus 2x squared plus x plus 1. Whatever it is, what we could write it as, first of all, we could just write it as p. Or we could write it as p of x to tell us what the variable is. But what we're going to do is we're going to plug in an operator, p of t. So if p of x happened to be x minus 5, then our p of t would be the operator t minus 5 times the identity operator. Remember, the identity is the one that takes iv to v for all v and v. Okay. And so this is a polynomial of an operator, and if instead we had maybe a different polynomial, q of x was x squared minus bx plus c, then q of t would be t squared minus b times t plus c times the identity. And this would be an operator. It could eat a vector, so q of t would be a map from v to v, because t is a map from v to v. So then, how is this a map from v to v? Well, what does it do? It takes a vector v and it spits out t of v minus b times t of v. This is a number, b. You can just scale a vector. tv is a vector again, because t spits out vectors. And then plus c times v, because the identity just takes v. So this is what you'd get. It's a vector again. It would be an element of v, which it should be. So that's what we're going to do with polynomials. Okay. Let me see if there's anything else that I'm missing. Yes, there is. So there's some key results. The key results to this chapter on polynomials include this one. So if lambda is a number with p of lambda, so now we're plugging in a number lambda to the polynomial and we get 0, we call it a 0 or a root of p, the polynomial. And if lambda has p of lambda equals 0, then also what we know is that p equals, so let's give it a variable, p of x equals x minus lambda times q of x, where q of x is a polynomial of 1 less degree. Okay, what's degree? Degree is the highest order, the highest power that occurs. So if we had like 4x squared minus 3x to the third plus x minus 2, the degree is 3, not because of this 3, but because of this 3. Okay. And then there's another result that will, so this will be really useful for us because eventually we're going to do p of t, and then this will be t minus lambda, and this will give us an eigenvalue, and the eigenvector will be q of t applied to some vector v. But I'm getting ahead of myself. So this is an important result. And this is if and only if. So actually, if lambda is a 0, then p factors, like we say it factors. Then p factors like this. And in fact, it's actually if and only if. So the other way is easy. If p factors like this, then definitely plugging in lambda would give us lambda minus lambda, which would be 0. So that way is easy. The other way is that if you have a 0, then it always factors like this. Okay, now what's another important result? Another important result is the division algorithm, which looks similar to this. For any polynomials p and q, we can divide. We can divide with remainder. We will use this in proofs, so you need to know this. Don't ignore it. What does that mean? It means that, let's say we divide p by q. So, okay, let me just show you an example. If we divide 11 by 2, then what we get is that 11 is equal to 2 times 5 plus 1. We call this the quotient. Upon dividing by 2, we get a quotient of 5, and this is called the remainder. Okay? And exactly the same way, we can divide, like how we divide 11 by 2, we can divide p by q. and then we get some polynomial f, I don't know, I'm just giving it a name, plus some polynomial r for remainder. And the same thing, f we'd call the quotient, and then r would be the remainder. So this would be like p of x equals, like these are all polynomials. We're multiplying polynomials here, and then we're adding polynomials. Okay, this is really important. Maybe like q has to be not 0. You can't divide by 0. Okay, that's fine. Because and actually the reason for that is that the remainder will always have degree. So the remainder polynomial will always have degree strictly smaller than what? Than the degree of the thing we divided by. Than the degree of the poly we divided by. Obviously, for the exact result, let's look in the book. This will be really important. So here's that one about it always factors. Each 0 of a polynomial gives you a degree 1 factor and vice versa. But then our new one here. Suppose p and s are polynomials. S is not 0 because we're going to divide by s. We divide by s, and we get the quotient plus the remainder, where this is really important. Pay attention to this. The remainder has degree strictly less than the thing we divided by, than the degree of that. Okay, and this is going to work because what we're going to do is we're going to say that there's a minimal polynomial, a min poly of some operator, and that will be p. Okay, and then we're going to apply the division algorithm, or no, probably it'll be s, because if we had a remainder, we're going to basically show that the remainder is 0 to show that things divide with no remainder, with 0 remainder. And to show that the remainder is 0, we'll use the minimality. We've chosen a polynomial of minimal degree s. And then because degree of r is always less than s, we can show that r will satisfy the same thing that this did. Anyway, you're not going to understand this right now, but you need to know this result. Don't ignore it. It is important. I think that's it. I already talked about this result, which is how it factors over C into all linear factors. Okay, that will give us eigenvalues. And then here is how it'll factor. This is the quadratic formula, essentially. And here is how it'll factor over R. We'll have some linear factors, maybe, and then we'll have some quadratic factors, maybe. Okay? So, and the quadratic factors will all satisfy this so that there are imaginary roots, which means we cannot factor this quadratic any further into linear terms unless we start using imaginary numbers, lambda and lambda bar, which we're not going to do because we're over the real numbers. Okay. So, good. That's my going over of chapter 4. Maybe just one last thing. Let me just show you the polynomial division algorithm, SQ plus R. So let's divide P by S. Okay, let's say that P, I'm just going to do an example right now. P is this. Plus 2x minus 3. Hopefully I can remember how to do this. And let's say we want to divide it by x minus 2. Okay? So what I'll do is I'll just do exactly what I would do in middle school or high school, but for polynomials. I'll ask, how does this divide into the first term? Well, I'm going to need an x squared, so that my x times x squared gives x to the third, and I'm going to need a 3. And so now I'll multiply this by this, and I'll get 3x to the third. That's why I wrote this one down, so that I would get this term. But then I also have a minus 2 times that, so it's a minus 6x squared. And now I'm going to subtract this whole thing away. And that becomes 0, which is the whole point of why I wrote this down. And then I have a minus x squared minus minus is plus 6 So I have a plus 5x squared plus 2x minus 3. Okay, now I just repeat the process. Now I divide x minus 2 into 5x squared, obtaining an x and a 5, and I need a plus. Yeah. Then I get a 5x squared minus 10x. I'll subtract. You don't need to know how to do this, but I'm just showing you to make it more concrete that we really can do this. We will only need it theoretically. We won't actually need to do this division. But let me just show you what happens. 2x's minus 10. Is that going to be 12x's? If I make a mistake, oh well. But now we put this in here. That means we need 12. Okay, 12x minus 24. And then we subtract, and we get minus 3 minus 24 is minus 3 plus 24, so 21. Okay, so what we're going to see here is that P is equal to S times 3x squared plus 5x plus 12, and then I think plus 21. Or maybe it's minus 21, but let's see, let's check. So what's my s? X minus 2. If I multiply these two together, then I'll get 3x to the third plus 5x squared plus 12x minus 6x squared minus 10x minus 24. And then what does that give me? It'll be 3x to the third minus x squared, and then plus 2x minus 24. And that's almost what I started with. That's almost P. This was P, remember? But when I add 21, I get the correct minus 3. So it really did work. Okay, so we can always do this. We can always divide one polynomial by another, yielding a quotient and a remainder with strictly smaller degree. The degree of r is less than the degree of the polynomial we're dividing by. Okay, sometimes we call this the divisor. This is the dividend, and this is the quotient, and this is the remainder. Okay.